One way to prepare ethers is by intermolecular dehydration of alcohols. This is the reaction of sulfuric acid with excess alcohols upon heating. In this reaction, the hydroxy group of alcohols is protonated, and another molecule of alcohol can attack this carbon, displace the water molecule, and form the protonated ether. The excess hydrogen is taken by the solvent, which is also ethanol, to form the target ether. Take note that this process will produce only symmetrical ethers. Primary alcohols dehydrate to ethers at a temperature lower than competing dehydration to an alkene. Here in the case of ethanol, different temperature levels may give different products. 180 degrees Celsius to form an alkene, and around 140 degrees Celsius to form the ether. These temperature values are expected to be different for different types of alcohols. But we can say a generalized statement that a lower temperature would be needed if ethers are desired. This process will not work for secondary and tertiary alcohols. This is because elimination is much easier and preferred for these cases. A very important and useful method for the preparation of ethers is called Williamson ether synthesis. It involves nucleophilic substitution of alkyl halides or alkyl sulfonates by alkoxides and aryl oxides. Alkyl sulfonates, shown here as a general structure, are also very good substrates for this reaction because the sulfonate group here are very good leaving groups. The preparation of alkyl sulfonates is beyond our course, but it is commonly employed in organic synthesis. Williamson ether synthesis often starts with an alcohol, and this alcohol is deprotonated via an acid-base reaction. You need a strong base that can remove a proton from the alcohol. I used here sodium hydride. The solvent is dimethylformamide. This process will readily form the alkoxide. Exposure of an alkyl halide to this alkoxide will result to an SN2 reaction, wherein the oxygen of the alkoxide will act as a nucleophile to displace the leaving group, here a chloride. The result is an ether. This process can be performed quite easily in our laboratories. As you see in this product, Williamson ether synthesis is a very good route to prepare unsymmetrical ethers. The reaction follows an SN2 mechanism, so best results occur for primary alkyl halides, which avoids an E2 reaction. In some cases, secondary alkyl halides may also be used, but the temperature must be controlled. The alkyl halide cannot be ARX, an aromatic halide, or tertiary alkyl halide. For the aromatic halide here, the displacement of Br is not very likely and will not occur in ordinary conditions. For tertiary alkyl halide, on the other hand, elimination will occur quite easily. The next reaction is called Alkoxymercuration demercuration. We already encountered this reaction in our discussion of alkenes. If you use this set of conditions and water is involved, the alcohol is formed. However, if water is replaced by an alcohol, the species that will attack the mercurinium ion would then be this alcohol. And for the case of this compound, in the presence of ethanol, this ether will be formed instead of this alcohol. Now to the chemical reactions of ethers. Ethers react by nucleophilic substitution. This is similar to alcohols, wherein the oxygen atom requires an initial protonation. The reaction involves concentrated hydrogen iodide or hydrogen bromide at high temperature. This requires very strong conditions, and in fact, even concentrated HCl or HF will not work. For an ether, 2 equivalents of the hydrogen halide is required, and each of the alkyl groups may form alkyl halides. For example, this ether, the preparation of which was described earlier, may react with hydrogen iodide. The oxygen atom will be protonated, and the iodide may form a bond with this R group, either via SN1 or SN2, to form this alkyl iodide and ethanol. Here, the departure of ethanol is favored because it is a weak base. Next, ethanol may still be protonated by hydrogen iodide, and a displacement of the water moiety will occur upon attack of the iodide nucleophile. Take note that iodide is a strong nucleophile in polar solvents. This is an SN2 process. The reason is that a primary carbocation is unlikely to form in this case. And so we formed 2 alkyl iodides. This substitution is SN1 if the R group is benzylic, allylic, or tertiary. It is definitely SN2 if the R group is methyl or primary. If one aromatic group is attached to oxygen, the other is an alkyl group, only one equivalent of hydrogen halide will react. This is because the aryl alcohol cannot be transformed to an aryl halide. For example, in this case, if you react it with concentrated hydrogen bromide, the product will be a phenol and ethyl bromide. Phenol is unlikely to react further. This is prevented by the aromatic ring. If there are 2 aromatic groups that are attached to the oxygen, it will not react at all in this condition.